Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to do Aromatic Systems Part 2, Section 2. And this is all about the reactions, the details of the reactions that you need to know for your exam. Now, there are 5 major reactions. 5. There's halogenation, nitration, sulfonation, alkylation, and acylation. Those are the 5 major reactions. Then there are sub-reactions, there are side reactions, things that you can do that are like not exactly from the major point of view, but they're still very important nonetheless. We're going to learn about them as well, okay? And that's what the bottom are all about, the bottom 3 that are left over, okay? So we'll talk all about that in this order. So before we begin, I just want to mention that you should know the general mechanism because it's the same thing over and over again. And I'm not going to keep writing it out. I'm just going to say it's the general mechanism and here's the basic flow. Okay? But you know how to write it anytime you need to. You could always do that same general mechanism that I showed you in the previous video. Okay? So let's get started. Let's take a look at the general flow. This is the summary of all reactions, including the 5. Here's the 5 right here. So these are our 5, and then we have some side things that we're going to learn about. Okay, and that's what this is showing us. So let me just show you real quickly. We're starting with benzene in the middle, and we can do halogenation, whether it be Cl or I or Br going onto benzene. We could do nitration, which is an NO2 going onto the benzene. That's called a nitrobenzene. We could do sulfonation, where we have an SO3H going onto the benzene. See that? And then there's a little side reaction that we'll talk about. There's alkylation. This is called Friedel-Crafts alkylation. And that's where we put an R onto the benzene. There are some rules here that we're going to learn about. There's acylation, where this is a C double bond O. Acyl is C double bond O. And we're adding that onto a benzene. And again, there are some rules to remember. Now, when you do alkylation or acylation, you could oxidize it to a carboxylic acid known as a benzoic acid, or you can get rid of this double bond O by using this reaction, and now you have this without the double bond O. See that? And then from here, you have side reactions that you can put a Br on the benzyl carbon, the carbon next to benzene, and then do things after you have a Br there. Okay? That's it. That's what we're about to talk about in a little bit more detail, but that's the summary of everything you're about to see. Okay? So, halogenation, nitration, sulfonation, alkylation, acylation. Those are the 5. Let's get started. Halogenation. The only thing I want to point out here is that, and again, when the mechanism is the same, maybe I'll show it to you once, and then that's it. So if we have, let's say, Br2, right? And now this is in FeBr3. Now the reason why is because if you think about what we have to accomplish in the first step, is we have to take an aromatic benzene and break it into a non-aromatic. That requires a lot of energy. Because remember how stable this is from aromatics part 1 that we talked about, right? So there's an electron flow here. It doesn't want to break. However, if you could get this positive enough, it will. It'll break. And that's what this is. This right here is a Lewis acid. All it's going to do is it's going to hang out next to one of these Brs, making it more negative, because if it's next to a metal, it's going to draw electrons towards it, and that makes the Br on the end positive. So without the FeBr3, there's really no reaction. But with it there, what happens is that we break the double bond and we pull in a Br, while the other Br leaves. Really, it's leaving and it's hanging out with the FeBr3. That's all. It's kind of coupling with it, but you don't have to really show that. So what we have now is we have a Br attached on, and now follow your electron. So if the double bond's here, now it's there, that means that the carbon below became positive, right? That's the one that became positive. And then the double bonds here and here are the same. They never change. Now, we know we have resonance, but we don't have to show right now. But you know that you can do that, shift here, and then that, shift down there. But you don't have to show resonance. This is what happens. And then finally, at the end, we're going to just close it back up. So as soon as we break the benzene, or we break aromaticity, the system is dying to go back. And it will very easily. It'll pop out the H from whatever you want to use, you can have a base, you can have Br minus, doesn't matter. Let's say Br minus, you pull off the H and you recreate your benzene. You recreate your aromatic system, and that's halogenation. Okay, so without this FeBr3, nothing would happen. Now it turns out that this benzene, if it was more reactive, and you'll learn about how that's possible later on, a few videos from now, then maybe you wouldn't need FeBr3. Okay, but if it's just benzene or something similar to that, like a alkyl benzene, then you definitely need FeBr3. Okay, so FeBr3 is simply a Lewis acid, and it helps drive the reaction. Now, alternative is Cl2 with FeCl3, or I2 with HNO3. And by the way, FeCl3 or AlCl3, same thing. Just like FeBr3 or AlBr3, they're just Lewis acids. They're just Lewis acids. That's all we're doing here. We're making them attract to the Br or Cl or I in order to get them to have the other halogen positive. That's it. So these are alternatives, and that's the end of this one here. Okay, now let's talk about nitration. So for nitration, if we have a benzene and we treat it with HNO3, nitric acid, in sulfuric acid, okay, so again, we need a strong acid with another acid in order to get this to work, because benzene is very stable. So we need to push the environment. The way we do that is by making things very positive, or driving the reaction forward that way. What's going to happen, as a summary, is that nitro is coming in. NO2 comes in. And I just want to show you how this happens. Although, as I mentioned in the very first video, the section 1 video, it's probably not going to come up where they ask you a question about this mechanism, but here is how it happens, just so you know in case it did. Okay, so HNO3 is where you have an N with 3 oxygens on it, right? So you have a double bond O, 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 and now one of them is negative. Let's say that one there, and one of them is positive, which is nitrogen. So there you have it. So nitrogen is positive, the oxygen is negative. Here's HNO3. Now, when you have sulfuric acid, H2SO4, what it's going to do is it's going to protonate. Now, I have to say that the way we're going to protonate this is slightly different than you think, because if I ask you what should be protonated, you would probably say that this should be protonated, right? Because it's negative, right? And that's probably what you would suggest to be protonated. But what we're going to do is somewhat of a cheat, although it's a justifiable cheat because of resonance. See, this has resonance to stabilize right now, and so this is negative sometimes, and this is negative the other times because of resonance here. But this one with resonance becomes positive, and you would have an extra positive here, and that's not really good, right? You don't want to have an extra positive and then a negative up here. So let me show you what I mean. If I was to draw the resonance for this, if I go like that and this goes up, then I would have this is positive, this is negative, this is nitrogen, this is negative, this is positive. Look at that. Would you ever draw that? No, right? You're not going to draw 2 pluses and 2 minuses. That's extremely unstable. And we always try to reduce the amount of separation of charge. So that's not going to happen. So for that reason, this oxygen on the left is actually a little bit more basic. Because look, this one can go through electron flow, and this can go up. And by doing that, we're not making any extra positive. It's staying the same. We're not making any extra negative. It's staying the same, right? Now this is negative, and this is neutral, positive, OH. So you see how these are identical? This is very stable. It's electron flow. This is very stable, which means that it's less basic on those oxygens. Okay, so even though it looked like we should protonate the O minus, what we actually do, and this is a long-winded explanation, but it's important to get the idea, is that we're going to wind up protonating this oxygen over here on the left. Now, what I'm going to do is I'm going to protonate and make it leave at the same time, so I could save a step. So, and you could do that on your test. So it's double bond O, O minus. But now look, if that O leaves, if this becomes H2O and it leaves, then this is going to be 2 plus. Because notice how the nitrogen lost its electron from oxygen? It's leaving. So what I'm saying is that this O is taking the bond and getting protonated by that H. Okay? So what that means is, an easy way to do it is to say that this N is double bond twice to O. Because if this goes here, while that leaves, the water leaves, right? Then you have this right here, NO. This is still positive.